United States of America. Right now, I'm a student at University of South Florida. This research, I collaborate with my mentor, Dr. Nguyen from Vietnam. Right. So my research is about the development of the monitoring system for bird nest in the Swiftlet house. All right. Uh, so um, the edible Swiftlet nest is a delicacy and a precious gift from nature because of its presumably high nutrition. There's a lot of research about um the nutrition in Swiftlet nest. So you cannot definitely you cannot replace it with normally food, but because of its specialty, a specialness, it is still a delicacy in many of these Southeast Asian countries. So the industry of harvesting this Swiftlet nest, edible Swiftlet nest, is very, very popular in Southeast Asia, especially in Thanh Hoa province in Vietnam. Um, so in the past, because living nature of the Swiftlet nest is at the high cave outside the beach. So it's very dangerous to harvest these nests. So in few decades recently, they opened an industry to raise the Swiftlet nest in the man-made house so that the human can, get the Swiftlet nest more safely and more efficiently. Right. So of course, this research have a setting in Vietnam. So I'm gonna focus on the species of squid net in Vietnam, right? So many provinces and cities have built the squid bird house to adapt it to the trending of harvest squid nest uh, in man-made house. Uh, right. So of course, there's a lot of subspecies of domestic swiftlet nest bird in the world, but mostly you will see the swiftlet nest called white nest swiftlet nest raised in Vietnam, right? Sorry, excuse me. So in this research, we using Lidar combined with SLAM as simultaneously localization system to localize the robot and um, detect where is the swivel nest in the house, right? So there's some of the research in the past about SLAM system and robot in general. Um, so the most simple basic form of localization of robot in an environment is to using the wheel odometry combined with inertial measurement unit, which is IMU. And from those data, we can use Kalman filter to decrease the localization error induced by wheel odometry, because there will always be error in the wheel odometry produced from the decoder. But even though we use Kalman filter, the error is still unbounded, right? So therefore, we need to use the third source data, mostly from LiDAR or mostly from camera to make the error bounded, right? So that there is some method, for example, the active beacons method use triangulation calculation from 3 or more transmitters, right? So they're gonna they're gonna um they're gonna put like beacons in surrounding of the environment, and the robot gonna be able to calculate the position of the robot um corresponding to the active beacons placed around the environment through triangulation calculation. Another method is using ICP, which is iterative closest point method. So the lidar or the lidar or the camera gonna return consecutive scans of the environment, and they're gonna cap so because it is considered consecutive scans, it's assumed that there's a large overlap of the environment in between the scans, right? So they're gonna calculate the nearest points from the first scan to the second scan, and then from that calculation, we can calculate how much the robot have moved in said environment. Right. So there are a lot of algorithm of SLAM system, right? For example, Hector SLAM, cartographer G mapping, which is optimized for lidar based system, or OpSLAM, RTAB map, LSD SLAM, LSDO, a lot of SLAM method for camera based system as well, because camera was it was popular before lidar, so there are more algorithm for camera based than lidar. So yeah, in the research there are also some comparison between these SLAM algorithm, and they are also available availably used in ROS robotic operating system. So it's right. So after the data points from SLAM from the lidar is returned, we need to also use filtering such as smooth filter or median filter to apply into the data, so that we have smoother data points. We can decrease the error from statistical error or from noise for better matching, right? Um, right. So because this research is focusing on, detecting where is the bird nest in the environment. So we also have to look into some classifying object from LiDAR when we, obtain the 3D mapping of the environment. So there's some research about, using ransack algorithm to extract the ground plane, because the robot moving on the ground, right? So they need to obtain the ground plane, the true ground plane, so that any above the ground plane, um, they're gonna consider it belong to the the object that they want to detect. Um, another another method is, instead of use ransack algorithm, they use fuzzy logic to classify lidar data to different fuzzies, and then they're gonna use methods such as lie segmentation, object segmentation to make them list square of the bounding box, for example, to detect the object. Right. So of course we use lidar to mapping, right? There are two type of lidar, 2D lidar and 3D lidar. Um, so if you have the 3D lidar, you just need to, it gonna um return the 3D coordinate of each data point, so that you have the 3D map of the environment. 2D mapping in the other hand just gives you, X X and Y in Cartesian coordinate system of the data points. But of course, there's some research such as they use 2D lidar, but combined with a mirror. So they're gonna change the angle of the mirror to to bounce the 2D laser from lidar to different height in the environment. So they can also obtain 3D environment 3D map from 2D lidar. So, right. So in our research, we also use 2D lidar, but we mount it to a feature that it can change its height. So we're gonna obtain different 2D map in different heights. So it's also a 3D environment mapping from 2D lidar. Right. So in the lab, we build the the model of the house of the Swiftlet house harvesting in taking from the reality so that we can provide measurement and provide experiment in the lab. All right. Yes. So here this is the model of the house. So of course the house is much bigger than this, but in the house they're gonna divide it the house into different squares or rectangular shape of each wooden frame so that the swiftlet bird can nest it onto these onto this wooden frame. So we only need to build one frame so that the robot can operate in that frame, right? So in our model, the length is 110 centimeters and the width is 50 centimeters. And of course, in reality, the each frame is each frame is on the rooftop, right? Because the bird gonna be nest in the rooftop. So we have to raise this model into by 4 steel posts so that it mimic the model in reality at best, right? And also we're gonna attach the bird nest randomly in the wooden frame, obviously. Right. So in the right, you can also see the 2D model, 2D representation of our robot in operation mode, right? So the robot gonna move in 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 the environment. The robot. So as you can see, we have 6 degree of freedoms. The robot gonna have 6 degree of freedoms, and so the on the right, the top right figure is the lidar mounted to the feature as I tell you. So this feature can change the height. It can retract. It can lengthen in height so that we obtain the the map from in different heights, right? In Z direction. So this lidar gonna it gonna we're gonna connect this lidar to the CPU control unit system that communicate with the CPU with computer through UART communication system, right? And this lidar gonna be rotate 360 degrees and with 0.1 or 2 1 degrees it gonna shoot the laser and gonna measure the laser so the distance of the laser gonna be XY of the data points in Cartesian, right? So after we obtain the data points from lidar, we need to you know um we need to apply some filter so that the noise is filtered and the the map is smoothening, right? So the LiDAR data can be affected by random noise, and systematic noise. So we're gonna obtain, we're gonna use filter to filter out the systematic noise and some random noise as well, right? So in the next slide, you're gonna see how we apply filter to reduce the systematic noise. Right. So of course, random noise and systematic noise gonna result in inaccurate measurement. That is obvious. Right. And here we are. So the graph in the left show you so if this graph show you the statistical error, the systematic statistical error in the LiDAR, corresponding to the data points, to the distance of that data points, right? So for example, if that object is at 2,500 millimeters, then they're gonna be 200 millimeters systematic errors, 200 millimeters in the XY coordinates, right? So that is because of how the manufacturer build this LiDAR, so it has its own error, right? So and also some of the factors that affected the errors, such as light intensity, the voltage, the um the current and the voltage we feed into the LiDAR also affect the error, right? So from this graph, we're gonna because as you remember, the model that we built for the harvesting the LiDAR, or it is small enough so that the systematic error is not that big, right? So we just need to make some true measurement and compare it with the measurement from the LiDAR, and then from that we can calibrate, multiply by a constant to calibrate the LiDAR. Right. So this slide just explain you how the LiDAR is communicated with the computer, right? So that I use the RP LiDAR Python library to obtain the data points from LiDAR from LiDAR through UART to USB that is connected to the computer, right? Right. So after all of the statistical error calibration, and we have the data points from LiDAR itself, use voxelization, which basically it is like a pixel. So in 3D it is a cube. So voxelization is to draw a cube around a data point, and then we're gonna calculate how many points is included in that cube. So if there is not enough points in that cube, then obviously that point is an outliers, because it not close to other points, which means it has high likelihood that it doesn't belong to an object that we intended to measure. And yeah, so we use voxelization, and yeah, and also we use instead of voxelization, we can also calculate, like, using the closest point approximation, to calculate the distance between this point to the closest point, to see is it is the that distance meet the requirement of being belong to the object, right? So in this slide, in the figure, you can see that this is the 2D um 2D map of the model when we put it in a specific height, right? So you, um you're gonna see that there's some so the straight line is the wall, and the cup shape, like not not that not that round to be considered to be semicircle, but it that resemble the model of our bird nest that we stick it into the model, right? So we're gonna so because there will be some hidden um hidden points, because we just put the robot stand still, right? So we need to move the robot around the model so that all of the angle is returned to the map, so that we obtain the better results, right? So here, in the bottom is the bird nest. So of course, in when this nest is handed to you, right, it's not gonna have that a lot of, the black spot, which is, some dirt. It's gonna be processed so that it truly edible. But this is the pre-processed of the edible bird nest, right? We're gonna attach it to the ball, and right. So in average, the net's gonna span from 850 mm length to 350 mm width. So we're gonna um move the robot around, and then the lidar gonna change its height and obtain each layer of 2D mapping with, and finally it results to the figure in the top, as you can see. Okay. So after excuse after we obtain the data points, we apply the line segmentation to into the data points, right? So um so in simple terms, we start with first point, right? And we're gonna actually we start with endpoints, and we're gonna calculate the best fit line through that endpoint, and using RMSE, root mean square error regression, using the regression method. And then from each point afterward, endpoint, we're gonna calculate the the distance from that point to the line, to see if it meet the threshold. If it meet the threshold, then that point gonna be included into that line, right? And if it's not included, then we start from that point plus endpoint, and then the algorithm gonna in the loop, so that we obtain many line segmentation from our model. So in our research, we choose n to be n the initialization point to be 4, and the threshold value that the next point is compared to is 4, because as you remember, the statistical error that itself induced in the lidar is 4 mm. So we put the threshold to be 4, so that we we um um we include the we understand the statistical error into the model. So after we obtain a lot of um line segmentation, we use ransack algorithm. It not it's so it's similar to ransack, but not exactly the ransack algorithm, right? So we so for every point segment as line, um an n random number of points are chosen to fit a line, right? And then we're gonna calculate the RMSE again, and we're gonna use this. So there's two methods, right? We can run the ransack algorithm um the the error is smaller than some threshold, or we can just run it in 100 loops, and normally it can also yield a good result as well. Right. And so this is excuse me, this is the results. So um so as you can see, right, in the that in the 2D mapping, there's a lot of points, right? So we're gonna use the segmentation lines to segment a lot of points to know that which point which point is in the line, and then we gonna use ransack to choose the best fit line, and that line gonna be sorry, that line gonna be the wall line. So the wall line is the blue line here, as you can see, and from the wall, we're gonna be able to obtain the nest, because it is far from the wall, right? So because the algorithm is start with the first point, and then gonna use the next closest point to um to see if it's belong to the line, right? We have to sort it in the KD tree data structure first. So in simple terms, KD tree data structure is just to move sorted the data into the list, that the first the second point is the closest point corresponding to the first point, and the third point is the closest point corresponding to the second point, right? So yeah, in simple terms, the KD tree is just to move it into the order of the closeness, and then we're gonna use line segmentation, and as I discussed in the previous slide, to obtain the figure in left. Right, so in the result, so in the red line, the red data point is the distance, is the size of the bird nest that we manually measure the hand, right? And the the blue point is the lidar scan data point. So as you can see, it has is bumble around, it's not smooth because of its statistical error. In mostly 4 millimeters because of its statistical error, but after we obtain the points that we believe to corresponded to the nest, and we use our the regression method to obtain the best curve through those lidar scan points, and we obtain not the shape to be pretty close to the manually measure. So yeah. So in conclusion, if you search for research for autonomous monitoring system for bird nest farming, especially in Southeast Asia countries such as Vietnam, China, Malaysia, Indonesia, that there's a lot of research, but about the nutrition of the swiftlet bird nest is right. So it's not so it's that's not you cannot find a lot of research about autonomous robot systems such as doing using a system to harvest the robot harvest the nest, right? So because of that, excuse me, because of that, we the improvement on autonomous tasks to harvesting the EBN is a must, because it's very necessary to have an autonomous robot system. Right. So more on why the autonomous robot system is necessary, right? Because firstly, when the human go into the man-made, for example, they also have to, climb up in the ladder, because the bird nest gonna be nested on the rooftop, and the bird itself doesn't like the smell of human, and and the the final purpose of building the man-made Swiftlet house is to attract more birds, come back to that house to, nest every year, so that we have, annually income, right? But if the bird doesn't like the smell of the human, it's gonna deter the bird to come back. So it is one of the reason why the robot system is more advantageous. Um, right. So in this research, we focus on recognize the bird nest and estimate its position. But the other tasks, such as compute the optimum track, for example, to harvest the bird nest, is not focused. So it is also one of the future route that we can go on, if we focus on building a truly autonomous task for EBN farming. Right. So to summarize, we develop an algorithm to take odometry, using SLAM, SLAM algorithm that is introduced in the slides, and then to localization in the environment, in the model that we built, and then we use the some of the methods, such as line segmentation, to build to obtain the local the position of the bird nest in that 3D map that we obtained. Okay, so this is just the reference that is referred in the research.